Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will executate on a teaching lesson which is of current electricity, and also we will highlight on some of the relevant terms pertaining to it. Now, we all know that the current electricity is very important and it has many variant technological applications. So in order to have a great concept of what constitutes current, we should know that when we apply potential across a wire through a battery, current will be flowing through that wire, or charges will be flowing through that wire. Now, according to the definition of electric current, we know that when charges are flowing, or when the electric charges are flowing in a conductor, and when these charges are moving in a specified direction, then that constitutes electric current. So we know that in a conductor might be aluminium, it might be solid conductor, it might be a liquid conductor, it might be aluminium. So if I consider that solid conductor, it might be aluminium, copper, it might be silver also, or it might be gold. Any of these solid conductors, they will have these free charges within them. We know that in a structure of an atom, we have the positively charged nucleus. Surrounding the nucleus, we have these electrons. If I consider that there are valence electrons, all these valence electrons will contribute to what is known as the free electrons. Free electrons. So it is this free electrons which constitute to the flow of electric current. So by definition, current is defined as the flow of charge per unit time. Flow of charge per unit time, or the time rate of flow of charge in a given direction or specified direction through any cross section of the wire. So that is defined as your electric current. The SI unit of current is that the SI unit of charge is coulomb. The SI unit of charge is coulomb, and SI unit of time is 1. The SI unit of time is seconds. So the SI unit of current will be 1. Current will be amperes. Ampere equal 1 coulomb per second. So 1 ampere is that 1 coulomb and 1 second, or when 1 coulomb of charge flows through a conductor in time of 1 second, then the current is said to be 1 ampere. See, 1 coulomb is equal to 625 into 10 to the power 16 electrons. And in a conductor, there are many number of electrons. So if I want to find the total charge within a conductor, so the total number of charge will be equal to integral multiples of E, or n times E, where this value of n will take integral values of 1, 2, 3, and so on and so forth. This concept also gives us a foundation about what we call as the quantization of charge. Charges in nature are discrete, or they are quantized. Quantization of charge. So if I want to find the magnitude of what is E, if you divide this 625, or 1 divided by 625 into 10 to the power 16 electrons, you will get this value of 1.6 into 10 to the power minus 19 coulomb, which is the magnitude of the charge of the electron. Now, always remember that this current is nothing but a scalar quantity. Okay, it is a scalar quantity. That means it measures only the amount of what charges flows through a particular area or a particular through a particular cross section. Always keep in mind that current is a scalar quantity. Okay. So now when we are dealing with this current, you should also know the direction of the current flow. Okay, we already have been aware that the direction of flow of current is always taken from the positive end of the power supply or the battery towards the negative end of the power supply or the battery. Now this direction of flow of charges is what we define as what? Current, denoted by I. But if I take a wire or if I magnify the cross-sectional area or the cross-sectional geometrical shape of the wire, it will be of this form. Now inside the wire we have what? We have many charges. Okay, we have many charges or free electrons. Okay, suppose, but all these free electrons which are inside the wire, okay, before you connect them across a voltage source, they will be moving in different directions. Suppose, let us do some illustration. Okay, let us do some illustration. Now inside the wire there are free electrons. Okay, that is number one. And all these free electrons, okay, all these free electrons are in the state of random motion. Inside any conductor there will be free electrons. Okay. All these free electrons will come from those valence electrons which I have explained to you. Okay. So all these free electrons in a wire or in a conductor, that means at room temperature, they will be in the state of random motion. At room temperature, they will be, all those free electrons will be in the state of what? Will be in the state of random motion. When they are in the state of random motion, all these electrons will suffer what? They will experience what there will be some collision. Okay? There will be some collision between the electrons. So when they are in the state of random motion, that means all these electrons are moving in different direction. Okay, all these electrons are moving in different direction, haphazard direction. So there will be collision among these electrons, and when there is collision among these electrons, there will be some thermal energy. Okay, thermal energy or thermal agitations. Okay, thermal energy or thermal agitations. But due to the random motion of the electrons, the average thermal energy of a conductor at room temperature will be equal to 0. Now, when you connect this wire across a voltage source in the form of a battery, what will happen? All these electrons will be moving not anymore in random motion, but they will be moving in a single direction. Okay, they will be moving in a single direction, or all the free electrons will be moving in a specified direction or unidirection. Okay, unidirection. It might be, or that means when I say unidirection, that means in a single direction. So this is the positive end of the battery and this is the negative end of the battery. So this end of the wire will be at a positive potential and this end of the wire will be at a negative potential. So you know that there will be free electrons on the wire, and all these free electrons, since you know that electrons are negatively in charge according to rules of electrostatics, that means the electrons will always attract. Okay, it will always experience Coulomb's electrostatic force of attraction. So it will attract this positive plate. So all these electrons will accumulate towards the positive end, or they will move towards the positive end. So this movement of electrons, okay, this movement of electrons towards the positive end will give rise or what we define as electronic current. And also remember that when you connect a wire across a battery, that means electric field will be set up, electric field will be set up in the wire. Okay, all these motion of the electrons which moves towards the positive end of the wire will be in a direction which is opposite to E. So all these free electrons, they move in a direction which is opposite to E. So they move in a direction which is opposite to the electric field, and they constitute to what we define as electronic current. Okay, as electronic current. But in addition to these electronic currents, since the conventional flow of current is always from positive to negative, that means we have these positive charge ions. All these positive charge ions of the individual atoms, constituting this metal or constituting that conductor, all these positive charge ions, they will be moving in a direction which is along the direction of E. They will be moving in the direction which is along the direction of E. So they will be moving on this direction. All these electrons, all these positive charge ions, they will be moving in a direction which is in the same direction of E. So all these positive charge ions of the individual atoms, they will move, okay, they will move in the same direction as E. And if they move in the same direction as E, when these positive ions move in the same direction as E, so this movement of positive charge ion is what we call as what? As our conventional, okay, conventional current. So electronic current moves in a direction opposite to E, whereas these positive charge ions, they will move in a direction along the direction of your electric field. So from here, the direction of the flow of current is along the direction of the electric field, and this is what is known as your conventional current. Conventional current is nothing but the movement of those positive ions. But don't get confused. The electrons are moving in a direction which is opposite to the current flow. Current I is moving in this direction, whereas electron flow is in a direction which is opposite to I. Now, there are some terms relevant to the motion of these electrons. In physics, when we are dealing with motion, that means these electrons should have some velocity. And when they are moving, we know that there will be one. We have written somewhere here that there will be some collision. When they are in the state of motion, that there will be some collision. Also, they will experience some time for which the electrons will move from one end of the conductor to the other end of the conductor. So these are some of the parameters that we need to understand, and we need to explain, okay, and ponder upon. So number one is the relaxation time. Okay, what is that relaxation time? Okay, so from here we know that when these electrons are moving, they will undergo one. They are sure to hit these they are sure to collide with the individual atoms or the corresponding atoms or the neighboring atoms. When these electrons are moving under the effect or under the influence of the electric field, they will have some velocity. This velocity with which they move, okay, towards one end of the conductor is what we define as the drift velocity, denoted by Vd. But during the course of journey, there will be some collision between the electrons. Okay, there will be some collision between the electrons. So from here, like for instance over here, suppose if I consider in this case, okay, that all these electrons. Suppose if this is electron number 1 and this is electron number 2, and let us apply an electric field across this wire. Okay, let us apply an electric field across this wire by the help of this battery having a certain potential. Now you know that these electrons, will undergo what? They will undergo collision between the neighboring atoms. Suppose if I consider this as E1 and if I consider this as E2. Okay, those are the two electrons under consideration. Now, when this first electron moves on this direction, that means it is certain to hit this electron. Electron 1 will hit electron 2. And from here also, it is evident that this is the motion, the direction in which the electrons are moving. So, this electron 2, upon the impact of 1, will hit another neighboring atom, electron number 3. So, there are two collisions over here. That means, if I say that let T1 be the time of impact by 1 on 2, and T2 be the time of impact of electron 2 on electron 3, that means the average time spent by an electron between two successive collisions, that is defined as what? That is defined as your relaxation time. There should be two successive collisions. And from here also, when electrons are colliding, they are moving through a certain time and they will be having some distance. That means from this point to this point, there will be some distance. From that point E2 to point E3 also there will be some distance. So the distance covered by the electron between two successive collisions, that is defined as your free path. Okay, free path. So from here, the distance between two successive collisions is defined as your free path. And what is this drift velocity? When the electrons are moving, all these electrons are moving in the direction which is opposite to E. All these electrons are moving which is in the direction which is opposite to E and towards the positive end of the wire. This velocity is defined as what? As the drift velocity. So from here, the average velocity with which the free electrons move towards the positive end of the conductor under the influence of the electric field is defined as drift velocity. So now we have to understand also what is electron mobility. So what is this electron mobility? Okay, when we assume a wire, and we know that electric field, the moment when you pass current, with the moment when you pass potential across the wire in the form of a battery, that means electric field will be set up. And all these electrons will be drifting or moving towards the positive end of the wire, having a certain potential Vd. So, which means from here that this drift velocity, it is solely and purely dependent or directly proportional to the strength of the electric field. When the strength of the electric field is large, the drift velocity also will be large. So from here we can come to the conclusion that if we remove this proportionality sign, we replace by a constant of proportionality. That constant of proportionality, this constant of proportionality is what we define as what? As our electron mobility. So what is electron mobility? Electron mobility, from that derivation, from this simple analogy, electron mobility is defined as what? Is defined as the drift velocity per unit what? Per unit electric field. Per unit electric field. So drift velocity per unit electric field is defined as what? As the electron mobility. So electron mobility measures the amount of how many electrons are moving in a conductor. So from here, this is the formula for electron mobility, and also you have to know what is the units of electron mobility. So from here, step by step, the units of the units of drift velocity is meter per second, and the units of electric field, keep in mind that electric field will be having the formula of force per unit charge, Also, electric field can be defined as the gradient. We have discussed about this. The electric field is defined as the gradient of the potential, dV by dr. So in this case, the electric field, okay, the electric field will be having the units of what? Newton, okay, Newton Coulomb inverse, okay, Newton Coulomb inverse. And in this case, the electric field will be having the units, okay, the electric field will be having the units of what? The units of volts per meter or volt meter inverse. Both these units, okay, both these units of E, electric field equal Newton per Coulomb, and electric field volt per meter are one in the same. Be careful, some of the multiple choice question will be asked related to units of electric field. Electric field, one definition is in terms of one. One definition will be in the form of force per unit charge, okay? Force per unit charge, or it might be electric field in terms of what? In terms of the gradient of potential. So from here, we will make use of this equation. That means from here, the SI unit of electric field is 1 volt, okay, per meter, okay? Volt per meter or volt meter inverse. And from here, that means when we simplify this one, you'll get meter square, second inverse, and volt inverse. Or you can, if you recall right from this step, that means what is this meter per second? Okay? What is that meter per second? What is this meter per second? Your meter per second is nothing but your SI unit of volts. Okay, SI unit of volts. So this is one way of writing. Okay, one way of writing it is meter square, second inverse, okay, volt inverse. Okay, meter square, second inverse, volt inverse. Okay, volt inverse. So this is the units. Okay, units of what? Units of our electron mobility. Electron mobility. Okay. So now we will move on into this another important parameter, or which we define as what? Current density. What is current density? In a given wire like this, you have a wire, and when you apply potential across this wire, or that means this will be positive end and this will be the negative end. All these electrons, they will be moving towards the positive end. Suppose if I consider a small elementary area, let that area of the wire be A. Okay, let that area of the wire be A. And when these electrons passes through this wire, or through that cross-sectional area, that means it measures the amount of what? Density. So by definition, this current density is defined as the current, okay, current per unit area. Okay, current per unit area. So the electric current passing through the conductor per unit area is defined as current density. So the SI unit of current density is ampere, okay, ampere per meter square, okay, ampere per meter square, or we can write as ampere meter square inverse, okay, ampere meter square inverse. So these are some of the illustrations that we need to understand, so that you will have a clear intuition of the characteristics and some of the terms related to current electricity. So remember, let us recall and do a summary of what we have learned. Drift velocity, velocity of the free electrons in which they move towards the positive end of the conductor. Then the time taken between the electrons when they collide with each other on the two successive collisions is defined as relaxation time. Then when you talk about the distance covered by the electron between two successive collisions is defined as here 1, free path. Okay, so this point number 3, point number 4 are important for a 1 mark question related to definitions, and even this point number 5 important for 1 mark question related to definition of current density. Just go through those lectures so that you will have a clear intuition concept. Thank you.